Okay, so you can see I have the pH scale in front of me here, and actually, I guess it's behind me now. But over here on the left-hand side, we have the acids, and you probably have learned that the lower pHs are acids. So we have 1, 2, 3, 4, 5, 6. Then we get to 7, and we call that neutral. Now, it's a bit deceiving because pure water is only 7 at 25 degrees Celsius, and we're going to look at that today as well. And then the higher pH, as you can see, we go up to 14, and we call those bases. It's also called the alkali or the alkaline solutions. Over here, we have the acidic solutions. Okay, so let me share the screen now. We'll jump right in. So I do have a little bit of a review here on the first slide. If you want to try that, go for it. This is showing the acid-base pair, so what we did yesterday. If you're pretty comfortable with that, you could skip it. But, you know, hit pause and give them a try. The answers are on the next page. So there's the next page. And notice the way they wrote the carboxyl group here. So CO2 instead of COO. I wrote down the other derivations of that down here, and that was in that sheet from yesterday. Okay, so we need our equation sheet now. So the equation sheet has a whole section on equilibrium, and most of it is devoted to acids and bases. The first two you could see are Kc and Kp, which we just did with equilibrium. Now we're going to have Ka, Kb, and Kw, which is going to lead us into something called pH. So what is pH? pH is the potential of hydrogen. That's what pH stands for. So pH is the potential. It's actually something in German. I don't remember the word. It also starts with P, but it stands for power. So the power of hydrogen, we refer to it generally as the potential of hydrogen, which is why it's always lowercase p and capital H, not lowercase p and lower h or capital P and capital H. It's always the same, lowercase p. And we're going to see something else with that lowercase p. It doesn't just apply to pH. For example, we have some other p's, pKa, pKb. Okay, so potential of hydrogen. So the potential of the hydrogen ion. So what we're really measuring is a potential of hydrogen, but even more specifically, we're measuring the concentration of the hydrogen in molarity. So our brackets are back. So molarity. So when we see those brackets here and here in our equations, we're talking about molarity again. All right, so pH is the potential of the hydrogen ion, and we're measuring the molarity of that hydrogen. All right, so here's the autoionization of water, and this is really where we start our discussion of pH, or where it begins, which is why I don't do it in first year chemistry, which I've said a few times now, because you don't understand equilibrium, and it's based on equilibrium. pH is based on equilibrium. The only time you don't have to worry about equilibrium with pH is with strong acids and strong bases, as you're going to see today. So that's the rarity, though. Most acids and bases are not strong ones. We have very few strong acids, for example, but we have hundreds of weak ones. So you can't do pH without equilibrium. So that's why I skip it, other than the scale. Okay, so now this reaction, and now I'm going to do the second one, not the first one, but you can see water, and it helps to think of water as HOH sometimes when we're doing this. So it has a hydrogen ion section, it has a hydroxide ion, and if you are to autoionize, that means it's automatically doing this. Now, the amount of water you have in this doesn't matter. You're going to see in a second. It could be just a beaker full of water. It could be a whole swimming pool full of water. You're going to get the same values with this. So why does the concentration of water not matter? That's what we're going to see as well. All right, so it's slightly endothermic, which means energy is over here on the reactant side. So it is affected by temperature. 25 degrees Celsius, you can see, would be right there in the middle between 20 and 30. And we know that at 25 degrees Celsius, it's 1 times 10 to the minus 14. As the temperature goes down, so to 20 degrees, to 10 degrees, to 0 degrees, you could see the Kw is also going down. Times 10 to the minus 15, times 10 to the minus 15, so 1 times 10, they're getting smaller and smaller and smaller. So if the temperature goes down, remember it's going to shift to the left. The exothermic reaction would be favored when the temperature goes down. That means you're going to have less hydrogen ions and less hydroxide ions as the temperature goes down. But notice as the temperature goes up, the Kw gets bigger. KW equals products over reactants. If the KW is getting bigger, that means you have more products, meaning you have more hydrogen and hydroxide ions as the temperature goes up. So as you change the temperature, it also affects the pH. We know the pH of pure water is 7. Well, that's only at 25 degrees Celsius. As you move away from 25 degrees Celsius, because this is an equilibrium and because it's endothermic, it's going to affect the pH. So pure water has a pH of 7, but that's only at 25 degrees Celsius. Again, another reason I don't like to teach pH in first-year chemistry. You can't understand that. We haven't discussed equilibrium even a little bit. So to say the pH is 7 is only true if it's at 25 degrees Celsius. All right, next, let's get to the equation. So I'm going to skip to the next page where I have my equations, and I'm going to talk about this autoionization more so than the other one. I prefer to add it to water. Now, why do I do that? Well, look at our Ka and our Kb values here that we're given. The equation of this one would be H plus. So we have the Ka, we have the products, H plus and A minus, over the reactant HA, and you get what's called now an equilibrium value, Ka. I don't like that one. Notice we got H plus. I prefer, as I said, adding it to water, because now you can see the acid-base pairs, which you do have to pick out. So instead of getting H plus, you get H3O plus and A minus. So the difference is you'd have H3O plus, not H plus, but again, synonymous. So you can see in their equation sheet, they did not add water to the acid. Here's my issue with the College Board a lot of times. The next equation is the Kb for bases. So they have base yields. Now it should yield, well, there's no hydroxide there. That makes it kind of hard. So it's not a hydroxide base, it's an organic base. They don't even tell you that. Not only that, they give you as the products HB plus and OH minus. So where did the hydrogens and the oxygens come from? Well, it came from water, but they don't include it in the reactions generally when they do it. So it would be, and they didn't include it with the acid. Really, it should be the base plus water gives you. So you can see the acid is acting as an acid and the base as a base. Much better representation. So that's why I prefer this one. I like the uniformity of it. You can pick out the acid-base pairs. When we start doing something called hydrolysis, you're going to understand the reactions a little better. So get in the habit of adding water, but understand both. All right, here goes. I have my autoionization of water. H2O plus H2O. You can see one out water is acting as an acid, one's acting as a base, and I get the conjugate acid and the conjugate base on the other side. I'm going to write the Kw. So Kw equals. Now, when I write the Kw, it's products over reactants. So the products over the reactants, but the reactants are water. We don't include water in our equilibrium expressions. It's a pure liquid, has a constant molarity. So we don't have to worry about it. It's already factored in. We just ignore it. So when I do my ice charts, because it's equilibrium, this whole side of the equation doesn't matter. It's pure liquid. We don't include those in equilibrium expressions. Same would be true up here if I were to do an ice chart up here. So this side doesn't matter. So notice what we get. Instead of H3O plus, you get H plus. All right, so in the beginning, you don't have any of that or any of that. Let's say initially, before it started to ionize. Now, as it ionizes, it's going to be plus X, and so you're going to get X and X at equilibrium. One-to-one stoichiometry. All of these are going to be one-to-one stoichiometry. If you showed all of these equations to first-year chemistry students, they think it would be easy because everything is one-to-one to one-to-one. But again, we don't yet know about equilibrium. All right, so now let's carry this over here. So the Kw, now what we're going to assume, if it doesn't say so, is it's at 25 degrees Celsius. X times X, X squared, take the square root of both sides, and X equals 1 times 10 to the minus 7. So this is 1 times 10 to the minus 7, and this is 1 times 10 to the minus 7, as long as the Kw is 1 times 10 to the 14, which is only at 25 degrees Celsius. So what starts to happen? Well, then we know also that the pH is 7. We're going to see how we relate these in a second. So right here, 25 degrees, again, there's our cutoff point right here because we're higher or lower going off from that line. So going down were higher temperatures, going up were lower temperatures. And you can see the concentration of H3O plus is higher as the temperature goes up. Why is it higher? Well, remember this thing was endothermic, had a positive delta H. So if the temperature goes up, it shifts the equilibrium to the right and you get more of this. If you get more of that, you can see the concentration goes up. 1.21 times 10 to the minus 7. If you keep the temperature going up, the concentration continues to go up. If the temperature goes down though, now the equilibrium shifts the other way and you get less of this. And you can see the concentration goes down, 8 times 10 to the minus 8. 3 times 10 to the minus 8, so the temperature is going down. Now notice the effect on pH. So we're going to talk about pH. So as the hydronium ion concentration goes up, you can see the pH goes down. So as you have more and more of the hydronium ion, the pH decreases. It goes down. Less and less and less. Smaller numbers. Well, think about our scale we just talked about. These were the acids, these were the bases. Right in the middle we said was 7. So as we get more H3O plus, we have a more concentrated acid. And you make your way down all the way to a pH of 1. Like I said, there's a pH of 0, and there's even negative pHs. But when we go in the other direction, when the temperature goes down, that means we have less hydronium ion, less of this because it shifts to the left. As you have less of it, you can see its concentration goes down and the pH goes up. So this is, on this side, less hydronium ion as the pH increases. So we don't even call it an acid, we call it a base, but that doesn't mean, as you're going to see, that we don't have hydronium ion. All right. Now, back to this. Let's do the equations. Do I have the equations here? Let me see if I have that equation. Nope. All right, let me go grab it. Okay, so back to the equation. So have an equation sheet in front of you, or print this, whatever you have to do. Okay, so let me show you how we get our equations that are here, because there's a few on here that you need that aren't on here. All right, so I'm gonna skip ahead a little bit. So we've already done the ice chart, and we have the Kw, H3O plus and OH minus. So this right here is our first equation that we need, because sometimes you're given the hydronium ion concentration and you're asked to find the hydroxide concentration. So all we do is plug in the Kw, which is 1 times 10 to the minus 14. And then, plug in whichever one you're given and solve for the other one. So, there's our first equation where we can actually do some math, and we'll see that. I want to get beyond that though, because I want to get to pH. So what is the definition of pH officially, or the formula? Well, the formula is the negative log of the H plus concentration. So pH equals the negative log of the H plus, or H3O plus. Remember, synonymous. So pH equals, so the potential of hydrogen. So if we see what we've done to this right here, what we've done to this is you take the negative log of it. So what we're going to do is take the negative log of both sides. Negative log of both sides. Now we have to know a little bit about logs, or you can just trust me, but that's how we get this equation. So there's our next equation we need, which is 14 equals the pH, the potential of hydrogen, plus POH, which is probably a new one, but that's just the potential of the hydroxide. So if you take the negative log of both sides, now this little p here, here's a little trick. When you see a p in front of something in chemistry, that means you took the negative log of it. Took the negative log of it. So we don't just have pHs and POHs. If you take the negative log of both sides, you get the pKw. And that equals the negative log of H3O plus, which is the pH definition, negative log of. Now, when you're multiplying logs, you add them. And so that's where that comes from. So going from this equation, let me erase my marks on my equation sheet. So let me make my eraser bigger. All right, so we have, here's our KW. So KW, first equation. And you can see they give you that KW is equal to. All right, so now we've taken the negative log of both sides and we have this one. But they don't have PKW there. PKW is something you need to know. So if you take the negative log of 1.0 times 10 to the minus 14. Well, if I get rid of the negative, if this isn't here, the negative, well, the log of 1 times 10 to the 14th would be the same as the log of 1.0 plus the log of 10 to the minus 14. If it wasn't a negative, let's say. It's a positive, same thing. What's the log of 1? This is an important thing to know. If you don't know the log of 1, put it in your calculator. Log of 1 is, drum roll, 0. Big thing to know. Got to know that. So the log of 1 is 0 plus the log of 10 to the negative 14. So if it's 10 to the negative 14 and I take the log of that, that cancels out the 10 to the, and it's just whatever the exponent is. So the log of 10 to the minus 14 is minus 14. Right? If I do log of 10 to the negative 14th, it is negative 14. Well, the pH, though, isn't just the log, it's the negative log. So if I take the negative log of all of this, so then we have the negative log plus the negative log, because it's still plus because we are multiplying. So it'll be the negative log of 1, which is still 0. It's just the opposite of 0. But now we have the negative log of 10 to the negative 14th. So the log of 10 to the negative 14, so you just cancel the 10. So now we're doing the negative log of 10 to the minus 14. So you cancel the 10, but now we're taking the opposite, and it is 14. And again, if you don't know it or you don't believe it, try it. So now we have the negative log of 10 to the negative 14th. And you can see now we get positive 14. So there's a little trick with logs that, again, I emphasize it when I'm teaching this. I just actually taught this to my daughter that's at Wilkes last week. And I also taught it to my daughter that's a junior at West, because they're doing the same thing that we're doing right now. And I think it's hugely important that you understand these logs, taking a little bit of time that it is to learn this. So as I just said, let's say we have 1 times 10 to the minus 14. If we take the negative log of that, so all of this cancels because log of 1 is 0. So log of 10 to the, that cancels that. And negative log of 1 times 10 to the minus 14, then is 14. Well, what we just found out before was when you are at 25 degrees Celsius, the H3O plus concentration is 1 times 10 to the minus 7. So what's the negative log of 1 times 10 to the minus 7? Well, it's 7. Same thing. If you look at my calculator, negative log of 10 to the minus 14 is 14. 10 to the minus 7 is 7. So that's why the pH of pure water at 25 degrees Celsius is 7, because the hydronium ion concentration is 1 times 10 to the minus 7. So as temperature changes, that changes, which is why pH is not always 7. All right, so what about this? I'll show you that as we're doing it. I'm just going to skip right back into our formulas because we're going to come back to logs, but we're going to do a couple problems first. All right, so back to this. So we have now, we've figured out this equation. Well, because now PKW, negative log, P is always negative log. So the negative log of 1 times 10 to the minus 14 is called the PKW, but it's equal to 14. And that equals pH plus POH. All right, so now back to this equation. I said if you know either of these two, you can calculate the other because you have the Kw. Well, now if you have either of these two, you can calculate the other because 14 equals pH plus POH. So pH plus POH. So then I'm skipping these two equations because I've already talked about it. So that P in front, remember, means negative log. The P in front means the negative log, but now we're doing the OH. So we have pH and POH. As long as you know one of those, you know the other one, because all you gotta do is subtract from 14. We've talked about this equation right here, the fact that the Kw is equal to H plus or H3O plus times OH minus, and it's equal to 1 times 10 to the minus 14. And then down here we have a couple other equations with P. We don't have to know these yet, but notice P negative log of the Ka, PKB negative log of the Kb, and then we also have a Ka and a Kb in here. We don't need those yet. We're going to deal with those after a few days. And then this one's going to come in after a few days after that. This one has to do with buffers. All right, so that covers all of the equations, but now we got to know how to use them. All right, so this is the application. So the application of these. All right, so there's all the equations again. And again, I'm just going to start solving them now, and you can see how it goes. You're going to have to let me know how this is going too, because I don't get to see you, so I can't tell. Now, here's what I meant by, here's something else I'm going to show you with logs. All right, so we're calculating the pH of each solution, notice at 25 degrees Celsius. It always will be, you're going to see, indicate whether the solution is acidic or is it basic. Now, you could just compare that to 1 times 10 to the minus 7, because that's a pH of 7. So if the hydronium ion concentration is greater than that, then it's going to be a pH lower. It's less than that, it's going to be a pH higher. But all you got to do is take the negative log. So the negative log of 1.8 times 10 to the minus 4. So now here's what I always teach at this point. Estimate that. What is it about? Well, ignore the 1.8. If you take the negative log of 10 to the minus 4, it is, please get it right, 4. Yes, 4. Negative log of 10 to the minus 4 is 4. But it's not just 1 times 10 to the minus 4. So how does this number right here affect our overall answer? Again, we're estimating our answer. So if we were just doing the log, so negative log of 10 to the negative 4, as I said, the answer is 4. But it's not that. It's the negative log of 1.8 times 10 to the negative 4. So now for me, I need to put some parentheses around that probably. And now I get, and that's like I said, I know there was something wrong there. This calculator doesn't like me to do that. I have to use scientific notation. So negative log of 1.8 times 10 to the negative 4. I just wanted to show you the way it looked on my screen. But you can see the answer to this one now, the pH is 3.74. So we estimated it to be 4, but that's only if it's 1 times 10 to the minus 4. Anytime you have a number here, and the bigger this number gets, the more this gets away from 4. So if it's 1 times 10 to the minus 4, it's 4. 1.8 times 10 to the minus 4 is 3.7. If we were to do the negative log of, let's say, 9.1 times 10 to the minus 4, so getting further away from 1, you can see then we get 3.04. And then if we were all the way down to 1 times 10 to the minus 3, oops, got my log 1 times 10 to the minus 3, you can see then we get 3. So again, estimated. Here's the first way they try to trick you. They're not giving you the H3O, they're giving you OH minus. So when I do the negative log of 1.3 times 10 to the minus 2, and again, I can estimate it, it's gonna be somewhere around 2, but a little less. We're not getting pH this time. We're getting POH this time because it's OH. So the negative log of 1.3 times 10 to the minus 2 is 1.9. 1 decimal is good enough when you do these generally. So 1.9, that's the POH. So then 14 minus that from our equation, 14 minus 1.9, and we get 12.1 for the pH. So the POH is 1.9, but the pH is 12.1. So this one is acidic because it's less than 7, and this one is basic because it's greater than 7. All right, so here's the equation we don't have on our equation sheet that we need. There's other ways to do this, but the best way to do this is to understand logs and understand this one equation that is not on your equation sheet. All right, here's our issue. Now we have the pH. And we're asked to find the H3O plus. So if I were to plug these in the equation, so pH equals negative log of the H3O plus. I know this is 4.80 equals the negative log of the H3O plus. So how do you get rid of the negative log? That's the question. So I'm not going to show you the mathematic derivation of this. I'm just going to give you the equation. If you want to see the mathematic derivation for it, come into a Zoom, I'll show you. Just memorize it. So I'm taking this equation and really this equation, so these same two, and I'm going to rearrange it the other way around. So the way we do this is do a 10 to the negative pH is equal to the H3O plus concentration. So if you want, I can show you the derivation, like I said, but it's best you just memorize them. So here's two equations that you just got to memorize. Notice not on the equation sheet. And when asked about this, because I've seen teachers ask the College Board about this, they say you should have the skills to do this derivation. Now, really, it's this equation right here rearranged. So I have the H3O plus, it's 10 to the, if you do 10 to the negative, so we're doing the negative of both sides. So you have negative pH equals the log. I said I wasn't going to show you, and I'm not showing you anyway, sorry. And now we do 10 to the. So 10 to the negative pH, 10 to the, that cancels the log. So there's where it comes from. Just so I'm not making it, just so you know I'm not making it up. All right, so now we can come back to this and we can just do the algebra. So we got to get rid of negative log. So as I said, you could take the negative of both sides. If you take the negative of both sides, and then 10 to the, or use the equation I gave you, which is H3O plus is equal to 10 to the negative pH. So it's equal to 10 to the negative 4.8. It helps if you have a caret button on your calculator. I do, so I don't have to worry about, I think most calculators do anymore. So 10 to the negative 4.8 is 1.6 times 10 to the minus 5. And that would be molar because it's brackets. I'm going to stop there because there's a lot still left to do with this, and I don't want to make this video any longer after you just did the review too. So I'm going to stop there. I'm going to give you a worksheet that has just some of these basic calculations like I just showed you. Before I show you the next part, let me show you where we're headed though, why I have to stop. So I want to show you this equation, this right here, and I'll finish it tomorrow. Okay, so let me just show you this quick, and then, like I said, I'll finish this tomorrow, and I'll show you it officially tomorrow. So if you don't want to listen, you don't have to, just go. All right, so the weak acid solution, so we have to be able to write the equations for this. So this is what I was referring to back in the beginning of this, where we have to be able to write. I'll show you this tomorrow again. So if you can't figure out what I'm doing there, that's what I'm going to start with tomorrow. Now notice we have an ice chart again, because it's a weak acid, we have equilibrium. So if this is 0.1 to start with, we don't care about water, 0 and 0. Minus x, this is 0.1 minus x, this is plus x, and this is plus x, and this is x and x, and now we have equilibrium, and now we have a Ka value. So if all of that looks familiar from now, we're going to ignore that minus x. So that's where we're headed. That's why I wanted to stop, because there's still a lot more involved. I didn't want to make this, 25 more minutes. So I'll give you a basic pH worksheet, and we'll pick up with this again on Monday.